Imagine that you're on a television game show and the host presents you with 3 closed doors.
Welcome to Let's Make a Deal! You have a choice of one of 3 doors. Behind one of the doors sits a shiny new Alien Institute sports car. Behind each of the other 2 doors is a smelly old goat.
After the host asks you to make a choice, you choose a door, say door 1, and you imagine yourself zooming around in your new AI sports car. After your choice of door 1, the host, aware of what's behind the other doors, reveals one of the other doors, say door 3, with a goat behind it. Now the host turns to you and says,
Do you want to keep your original door, the door you chose, door 1? Or, after seeing door 3, do you want to switch your choice to door 2?
What do you do?
Welcome to Alien Institute.
So again, there are 3 doors. Behind 2 of the doors are goats, and behind one of the doors is a car. You get to choose a door to win the car. You chose door 1, and before they show you whether you won or not, the host shows you door 3 with a goat behind it, and then asks you if you would like to change to door 2. So your decision is to keep your original door or switch. This game of probability that I remember from university has come to be known as the Monty Hall Problem, since it slightly resembles the 3 doors shown on the game show The Price is Right. This gaming question wasn't exactly new. In 1889, Joseph Bertrand presented a similar problem called the box paradox. In 1959, a similar 3 prisoners problem arose. And in 1975, the problem was presented in a letter to the editor of the American Statistician. Although probability theory has been around for a long time, most notably Christian Huygens' 1657 written treatise on probability theory, the problem about a car and goats hidden behind doors really came to life in 1990 when Marilyn Vos Savant revealed the question correctly in her column. It brought a firestorm of dissenting responses, and subsequently the New York Times reported it in their newspaper on July 21st, 1991. If your response to the 3 doors problem is to keep the original door that you chose, it's not an uncommon decision. But what might be interesting to the decider is that the odds improve if you change doors. There is something to be said about the psychology behind the idea of not wanting to give up something that you already have. But logically, it must be pointed out that just because you have it doesn't mean it's good. In other words, you have chosen a door, but there's no guarantee the car is behind that door. As a matter of fact, the odds are it isn't. Focusing on putting the true probability in your favor is important to making good decisions. especially over the superstitious idea of keeping your initial choice due to fear. Fear of losing something you never had. The false idea of being sick to find out that the original choice had the car after you changed. I'll say it in a different way. The belief that you had the door with the car initially and then changed to the losing door, the goat, is most likely coming from an instinct of fear. But also, it's coming from an incomplete intuition. Your intuition is immensely valuable, but you will learn today how to challenge that intuition in different ways to lift it to new levels. So yes, if you want to increase your probability of driving a shiny new car, the best decision in our scenario is to change doors from your original pick. Think of it this way. The game is set up for you to lose on your first pick, with only a probability of 1/3 to win. Staying with your choice keeps your probability at 1 out of 3. Now, if we look at our opportunity to change, we must look at it carefully. First of all, don't look at it as if you might lose something you had, because you never really had it anyway. The other misstep would be to look at it as a new game that is 50-50 after one of the doors was revealed with a goat. This is a fallacy because the host is not randomly choosing a door. If he randomly chose a door, he could accidentally open the door that has the sports car. The best way to look at this problem always is as the original problem. In the original problem, there is the chooser and the house. Call the house anything you want, the casino, Vegas, or the side that benefits when you lose. So at the beginning of the game, you as the chooser have a 1/3 chance of getting the sports car, and the house, who wants to keep the car, has a 2/3 chance of keeping it. Essentially, you choose one door, and by default, the house gets the other 2 doors. Now, when you have the opportunity to switch from your original choice, you are changing your probabilistic position from the 1/3 chooser to the 2/3 house. You are actually betting against your initial choice and moves you to a 2 out of 3 chance. If you think about it, by switching, you have chosen 2 doors rather than 1, and our probability of success will always increase with more choices. It's true that the house makes it appear to be your original pick versus the new pick, but the curtain that was cleared away was a potential winner at the beginning of the game. And the house cleared it away because only the house knew the bad choice, the goat choice. Take a look at the similar game I set up here, and then I'll really push the point home with 100 doors. So here we have 10 cups, 9 of which have 1 penny under them, but one of them has a $100 bill. Oh yeah, speaking of a penny, don't forget to take a look at this video right here. $1 million or a penny doubled after watching the rest of this video. So back to our game. 9 of the cups have a penny under them, and 1 of the cups has a $100 bill. Now, suppose I ask you, choose one of the cups to try to get the $100 bill. And suppose you choose cup number 3. So then what I do is I say, let me show you cup number 1. Cup number 1 has a penny. And I say, let me show you cup number 2. That has a penny. You chose 3, so I'm not going to show that one. I show cup number 4. Cup 4 has a penny. And cup 5 has a penny. And cup 6 has a penny. And cup 7 has a penny. And then I show you cup 9 has a penny. And then I show you cup 10 has a penny. Now at this point, I ask you, would you like to stay with your original cup that you chose? Or would you like to change? And your choice was, after really thinking about it, you said, let's change. And I say, here's what you would have won on cup 3 was the penny. And here's what you win today. $100. All right, let's really push this point home. Let's imagine a similar game, but this time we have 100 doors. Behind 99 doors are goats chewing on weeds in a room. And behind one door is a room with a shiny Alien Institute sports car. As a contestant on the show, you choose one of the 100 doors. Say you choose door number 74, the highlighted door among the other doors with the arrow pointing at it. Now, as in our 3-door game, the host reveals 98 doors with goats behind them. Their heads peek out from the 98 different rooms from where they were eating weeds. This leaves the closed doors number 74 and one other door that you didn't choose. Say door number 23. All the rest were opened and there were goats in them. So, one of these 2 doors has a goat and the other has the Alien Institute sports car. Now the host gives you an opportunity to change. You can keep your original pick of the door number 74, or you can change to door number 23. What do your instincts say now? Do you believe it's a 50-50 game now? Or are you pretty confident, say 99% confident, that the sports car is behind door 23, and you surely choose to change doors? By switching, you became the house and are probably driving around now in your Alien Institute sports car. In a sense, you chose all 99 doors as if you chose them at the beginning. Just remember, you didn't know that there were goats behind those other 98 doors in the beginning. If we play the game with 1,000 doors, then our probability improves to 999 doors out of 1,000. The more doors we add, the better our probability gets. We now go back to the original game where you picked door number 1 and were shown a goat behind door 3. So now, with our newfound knowledge, we decide to change to door 2. Door 1 opens, and there we see a smelly goat. Door 2, our new pick, is shown, and there it is, a much wanted Alien Institute sports car. Changing doors will win us a sports car approximately 66% of the time in our 3-door scenario. To show this, I wrote a program in Python to simulate 100 games played.
Hello world.
By switching, you can see the probability of winning the car by switching is 65% with our simulation. One last mathematical thing I need to mention before we go, and that is Bayes' theorem, named after Thomas Bayes. The first time I showed this was because a student asked one time if this problem could be solved using Bayes. Quickly I said yes, but when first attempting it, it really felt like sticking a square peg into a round hole.
I got a bad feeling
But with
about
patience,
this.
I was able to muscle through it. Bayesian methods are used much in biostatistics, among other areas of science, and often the problems fit the formula nicely. Bayes is often useful because the probability of an event can change as new information comes in. The new information adjusts the initial probability. In the future, when we cover probability, we will cover many problems involving Bayes' theorem. Again, Bayes describes the probability of an event based on knowledge of conditions that are related to that event. To simplify, suppose I have 9 red poker chips in a hat and 1 blue chip. Now, you see me pull a blue chip out of the hat without replacing it, leaving 9 chips in the hat. So given that knowledge, you know now, because there are only red chips left in the hat, that there's a 100% chance of pulling a red chip out of the hat on my next pick. So let's apply Bayes to the 3 doors problem. Don't worry if Bayes is not crystal clear in this example. Just try to follow along. Like I said, we will build off of smaller examples down the road. Okay, so Bayes' theorem looks like this using A and B as events. The probability of event A happening given event B has already happened is equivalent to the probability of B given A times the probability of A divided by the probability of B. But there's an alternative form that we're going to use today, and that is the probability of A given B is equivalent to the probability of B given A times the probability of A divided by the probability of B given A times probability of A plus the probability of B given not A times the probability of not A. And since we're talking about doors in the Monty Hall problem, what we're going to do is replace the A's and B's from our general formula here with door numbers. Now keep in mind, this is a complex problem, so we're going to try to explain the steps as best we can, but normally it would take much more time and the learner would really have to reflect on every situation that's going on here. So what are we interested in? We are interested in 2 outcomes. We will call them stay for stay with the original pick, which was door 1 in this case, and change for change to the new door, which is door 2 in our case or in our scenario. So written mathematically, they look like this. Now keep in mind, Monty cannot open door 1 because that is the door the contestant has chosen. And he cannot open the door with the car behind it. Those are the rules. Now also keep in mind that Monty knows where the car is at the beginning of the game. So what is our formula for stay? Let's read the formula for stay. Stay equals the probability that door 1 has the car given Monty opens door 3. So our Bayes for stay using our alternative form will be stay equals the probability that Monty opens door 3 given door 1 has the car times the probability that door 1 has the car divided by the probability that Monty opens door 3 given door 1 has the car times probability that door 1 has the car plus probability that Monty opens door 3 given door 2 has the car times the probability that door 2 has the car plus the probability that Monty opens door 3 given door 3 has the car times the probability that door 3 has the car. Now notice the denominator, the normalizing constant, is partitions giving all possibilities of door 3 being opened, but they do not overlap. This is because door 3 was shown to have the goat. Note that door 1 either has the car or it does not. If door 1 does not have the car, that means in our case door 2 has the car. So it comes down to these two things. Either door 1 has the car or door 2 has the car. So now let's take a look at the change formula. So change is equal to the probability that door 2 has the car given Monty opened door 3. So using our alternative formula, this will be the probability that Monty opens door 3 given door 2 has the car times the probability that door 2 has the car divided by the normalizing constant. So the normalizing constant we just covered, and that's exactly the same as the stay. So the denominator in the change formula and the stay formula are exactly the same. So you can see them right here. Now, the same normalizing constant for the change denominator, well, since the denominators are the same, then we could determine which one had the greater probability between the door 1 and door 2 by just looking at the numerators. But we want the exact probability. So we're going to go the whole distance to make sure we get the exact probabilities. So here we go with that. Now, to get the exact probabilities of stay and change, let's describe the individual probabilities, or the components of the formulas, some repeating, and then calculate them on the worksheet that I'm going to be showing you. So the stay equals, looking at the formula at the upper left-hand corner, we have the probability Monty opens door 3 given door 1 has the car. So what is the probability that Monty opens door 3 given door 1 has the car? Well, if door 1 has the car, that means there's a goat behind door 2 and there's a goat behind door 3. So Monty could open door 2 or door 3. It doesn't really matter. He had a 50-50 chance. He just happened to open door 3. So since he had a 50-50 chance of opening either of those doors, we will put 1/2 in that slot. Moving to the right, the probability that door 1 has the car. So this is at the beginning of the game, before any doors were open. What's the probability that door 1 has the car? And that would be 1/3. It's going to be 1/3 for all the doors. They all have a 1/3 possibility of having the car at the beginning of the game. So we put a 1/3 in that slot. Moving down to the denominator, lower left-hand corner, probability that Monty opens door 3 given door 1 has the car. We already discussed that in the numerator. Again, if door 1 has the car, that means there's a goat behind 2 and there's a goat behind 3. So Monty can choose either door 2 or door 3. It's a 50-50 chance. So again, 1/2 goes in that slot. Moving to the right, probability that door 1 has the car. We discussed that all doors at the beginning of the game have a 1/3 probability of having the car behind it. So probability that door 1 has the car is 1/3. Moving to the right, plus probability that Monty opens door 3 given door 2 has the car. So now door 2 has the car, so Monty can't open door 2, and he can't open door 1 either because that's the door that the contestant had chosen. So Monty, by default, is forced to open door 3. So the probability that Monty opens door 3 given door 2 has the car is 100%, or 1 in probability world. So we put a 1 in that slot. Moving to the right, times the probability that door 2 has the car. Well, at the beginning of the game, all doors have equal probability of having the car, and there's 3 doors, so that's 1/3. So probability that door 2 has the car is 1/3 in that slot. Moving to the right, plus the probability that Monty opens door 3 given door 3 has the car. Well, if door 3 has the car, Monty's not allowed to open it. He can't open the door that has the car behind it. So the probability that Monty opens door 3 given door 3 has the car is 0%. So we will put a 0 in that slot. Moving to the right, probability that door 3 has the car, that's 1/3. It's just like the probability that door 1 has the car and the probability that door 2 has, they all have equal probability at the beginning of the game before any doors were open. So probability that door 3 has the car is 1/3 in that slot. Now doing the mathematics here, we have 1/2 times 1/3 in the numerator, giving us 1/6. And in the denominator, we have 1/2 times 1/3 plus 1 times 1/3 plus 0 times 1/3, which ultimately gives us in the denominator 1/6 plus 1/3 plus 0. Doing the addition in the denominator, we get 3/6. And now we have 1/6 divided by 3/6. Since it's division, we use the reciprocal. 1/6 times 6/3 giving us 1/3. So the probability of, at the beginning, if you do not choose to switch, if you stay with your original pick, is going to be 1/3. So in this case, door 1 was chosen, and if you stay with door 1, your probability will be 1/3. Okay, moving to the change. Now the change formula, as you look at it, there's a lot of the components that are exactly the same as the stay. In the denominator, everything's identical except for they're in a little bit different order. And in the numerator, you have a different numerator for the change than you do for the stay. So since the denominator is going to be the same number, we won't redo that one. And then let's just relook at the numerator here. So in the numerator, we have the probability that Monty opens door 3 given door 2 has the car. So we discussed that in the stay components. But if door 2 has the car, and then Monty can't open door 2, and the contestant chose door 1, so Monty can't open door 1, so he's forced into opening door 3. So that's a 100% chance that that's going to happen. So we put a 1 in that slot, and then moving to the right, we'll make that quick. Probability that door 2 has the car, we've discussed that over and over, so that's 1/3. So looking at our numerator, we have 1 times 1/3. Looking at the denominator, we have the same denominator as the stay, but in a little bit different order. And so we get 1/3 as the numerator after we multiply, and then we get the 1/3 plus 1/6 plus 0, we get the 3/6 in the denominator. So 1/3 divided by 3/6, use the reciprocal. 1/3 times 6/3 is equal to 2/3. So by switching, by changing from door 1 to door 2 after the goat was shown in door 3, by switching, you improve your probability. You improve your probability up to 2/3. So using Bayes' theorem, your probability of winning the car by staying with your original pick is 1/3, and your probability of winning the car by switching your pick is 2/3. But we already knew that from what we did before. Well, that about wraps it up from all angles. The best takeaway from the 3 doors game is the idea of challenging your instincts. Yes, instincts are valuable. Imagine if a bird didn't have the instincts to build a nest or migrate before the winter season. Think about humans. They instinctively have a fear of falling, and for good reason. But sometimes our first impression or perception can be a little myopic. It's possible we're not seeing the full picture. The blind men and the elephant story comes to mind here. In that story, each of the blind men thought the elephant was something else based on the part of the elephant they felt. The elephant's trunk was a thick snake. Its leg was the trunk of a tree. The ear was a fan, and the tail a rope. Essentially, the parts need to be put together in the right position and order to get the correct picture. It's important to form conjectures, but it's equally important to test and seek out more information to improve the picture or model. Use your integrated senses and mind to observe, then develop a theory, test that theory, and then make adjustments. Keep going through that cycle, and your model of reality will get closer to the true reality. Mentally walk around the problem presented to you. Challenge your intuition, because when you're circumspect, sometimes literally walking around the observation can get you to find out that the shadow of the square you saw on some wall did not come from a cube, but from the side of a cylinder. An impressionist's painting may just be a bunch of dots, but from a distance they turn into a scene of people and objects. And the water we drink can be broken down into millions of H2O molecules. The main thing is to look at problems in different ways. Break the problem apart and put it back together in clever ways. Sometimes it's a simple solution, Occam's razor, and sometimes the solution is complex. For our 3 doors problem, it became easier to understand when we expanded the model to 1,000 doors. The picture became more obvious with a greater number of doors. Other times, it's better to shrink the model. For instance, if someone asked me the probability of flipping a coin and getting 20 heads in a row, I would first begin to solve the probability of flipping 3 heads in a row. It's an easier problem to calculate. I guess what I'm saying here is to keep those brain cells firing. Get them fired up every day. There are so many problems that need to be solved. And here at Alien Institute, all of us together, including you, are dedicated to strengthen our minds to solve those unsolvable problems and unravel the mysteries in the universe in which we live.
Hey, Alien Institute crew! Don't forget to strike the like, subscribe, comment, and share. Also continue learning by watching more AI videos.